Hello everyone, welcome to my series on probability distribution. So today we are going to talk about the Bayes theorem. Now this is probably one of the most important topics of probability distribution that you will ever encounter. So I will go through it in detail. That's number one. And number two is often there are very complicated things like prior, posterior, and all those things people like make a big deal of. So I will try to make things extremely simple for you in this video. So let's dive in. So this is the formula that people show you when they talk about Bayes theorem. Probability of A given B is equal to probability of B given A into probability of A divided by probability of B. This is what people show you in Bayes theorem. So what we are going to do is we are going to prove this theorem first using some Venn diagrams and some real mathematics so that it's very intuitive to you and you don't really have to memorize this formula. So let's dive in. So let's see an example where U is the set of all men, A is the set of men where the men are handsome, and B is the set of men where the men are rich. Now I am talking about A and B because this formula contains A and B, but we can transform A and B to handsome means H and rich means R. So that's what we are going to do. So we now have probability of H given R, and we have this formula right here, which is exactly the same as this formula. We have just replaced H by A, and we have replaced B by R. That's it. So this is a Venn diagram. So this is the Venn diagram for rich. This is the circle for handsome. And then these are people who are neither rich nor handsome. So you can see that there are four people who are both rich and handsome right here. There are five people who are rich but not handsome. These are these people. And there are two people who are handsome but not rich. And then there are the 10 unfortunate ones who are neither rich nor handsome, right? Okay, so let's try to get the probability of H given R. That means probability of someone being handsome given that they are rich. So we are saying that given that they are rich, that means they are rich, right? That means they are handsome and rich. So we can write it like this: they are handsome and rich given they are rich. So this is just a small hand form of this whole expression. I feel more comfortable with this notation. That is why I'm writing this here first. So who are these people basically? People who are rich and handsome are actually these people given rich. That means this entire circle right here. So we have four people who are both rich and handsome, and we have total how many? We have total nine people who are rich. So we can just count through the counting. We can count the number of rich plus handsome people, and we can count the number of rich people. If we do the division, we are going to get the probability. So nothing complicated so far, right? Okay, so let's move forward. So we have this table, we have this thing, we have calculated this so far. Now we can do something interesting. What we can do is we can divide this numerator and the denominator with the total number of men. So there are total how many men are there? 4 plus 5 plus 10 plus 2, whatever that is, we can divide by that, right? So no harm done. And you can see that this is a probability, this is another probability, and we can replace it like this. Now, we have not really come to the formula that we wanted to come to. This is not the Bayes theorem formula. The denominator is correct, but the numerator has still some modifications to do. So we are going to do that. First of all, let's do one thing. We have written the formula for probability of handsome given rich. Let's write the formula for probability of rich given handsome. Same thing. We are doing the exact same things. Convert into probability and voila, we are right here. Okay, fine. So far we haven't violated anything. We haven't done anything complicated. So the next thing we can do is we can write the numerator probability of R and H. That means probability of being rich and handsome right here is equal to probability of H given R into probability of R. So we can just multiply this one with this one, right? Same thing we can do right here. We can multiply this one with this one, and we are gonna get probability of being rich and handsome. Okay, so both of these things are equal, right? Both of these things are equal. So we can just write the right-hand side equal to this right-hand side. So that is what we have done here. And finally, we can just swap side, and this is basically our Bayes theorem formula. So do remember, right? This is our Bayes theorem formula. Now understand that we have derived this very easily. Some people do some crazy things by drawing some overlapping subsets and things like that, but that's not necessary. So this is very simple proof, and I think you have understood how Bayes theorem formula comes from. Okay, fine. Let's do one more modification. So we have probability of R right here. This can be written like this. So probability of R is equal to probability of being rich and handsome. So handsome can have two possible cases. someone can be handsome, that means yes, he is handsome, and someone can be not handsome, so no, he is not handsome. If you simply add the probability of those two cases, that means probability of being rich and handsome plus probability of being rich and not handsome, then you are gonna get probability of R. Now this is very simple. If you have idea about probability, you know that this is the idea of marginalization. And probability of R comma H, this can be written like this, and we have seen this right here as well, right? Okay, fine. So final formula is this one for probability of H given R. We have replaced probability of R by the formula right here, and also you can write this like this. So it's the same thing. So understand that the numerator and the denominator are the same here. It's just that the denominator will have to have all possible values of being handsome. So here the person can be handsome or the person cannot be handsome. Those two cases. Here also the person can be rich or the person maybe is not rich, right? Okay, fine. So we have done with Bayes theorem formulation. Fine. Now let's go to the important things. Let's look at a real example, right? Because I mean we need to be able to use this in real life. So suppose we have two coins. So one coin is uniform, that means the probability of head is 0.5, and the other coin is biased. That means the probability of head is 0.7. So 70% times it land heads and 30% times it will land tail approximately basically. Okay, now one of these two coins were tossed 100 times. And after tossing that coin 100 times, we got 60 heads and 40 tails, right? The question is, which coin was it? So we had two coins, we know their probabilities, and one of those were tossed, and we have the data for that, but we don't know which coin was tossed. We need to predict that coin. Okay, so it's very simple. First of all, let's explain this. So we need to get the probability of y equal to u, that means the coin being uniform, given the data that we have. So these are observations. We have observed these events. So given our observation, and we also need to get the probability of the coin being biased, given whatever we observed right here, 60 head and 40 tails. So if we have this probability value as bigger compared to this one, then we are going to say that the coin was uniform because this is more probable to happen, right? On the other hand, if we get this value as bigger, then we are going to say that the coin was biased, most likely, right? Okay, now let's see how do we calculate these things. So this is nothing but Bayes theorem at play. So that's why I've just written Bayes theorem here. No magic done here. So the important thing is we need to know what each of these terms are called in machine learning or in real life, right? This is called a posterior. This is called likelihood. This is called prior. And this is called normalizing constant. So the first thing is this thing right here, the posterior, we can sort of approximate it using only the numerator. Why? It is because you can see the normalizing constant that is right here below, it is actually the same for this one and for this one. So for comparison, it doesn't have any value because it is the same thing. So you can omit this completely. Okay, next thing is this, the prior. So you have the prior right here, right? Probability of y equal to b and probability of y equal to u, it is the prior. Prior means the probability of belonging to the certain class. So here the uniform coin or the biased coin. So the probability of the coin being uniform or the probability of the coin being biased, we are assuming that it's the same because we have one uniform and one biased coin. That's why. So if we had like 20 biased coin and maybe 10 uniform coin, then it would be different. We could have a different prior, but otherwise the prior, we can set it as equal. Since this is also equal, the prior also doesn't carry any importance in this problem. So the most important thing that we want to discuss now is the likelihood, right? Is the likelihood probability of d given y equal to b or y equal to u, basically right here. Okay, so probability of d given y equal to u, what does that mean? That means that given that your coin is uniform, suppose your coin is uniform, in that case, what is the probability of the data being generated? So what is the data? The data was this, getting 60 head and 40 tails. So we can simply use the binomial distribution. I already made a video on the binomial distributions. I have provided the link in the description. So we have 0.5 to the power 60, 0.5 was head probability, and we have 1 minus 0.5 to the power 40. So this is a probability of landing tail, and tail was done at 40 times, and this is the combinatorial factor. Same thing goes for the biased coin. So if this data came from the biased coin, then we would have 0.7 in the head probability and 1 minus 0.7 in the tail probability. Fine. Now, The thing is, this combinatorics term, we don't really need it because it's the same in both cases. As I said before, since we're comparing, we don't need the same things. So we can just calculate this one and this one. And we are going to see that this value right here is bigger. Since this value right here is bigger, this is basically our class. So we can say that the coin was actually uniform, right? The data was generated from a uniform coin and not the biased coin. Now, this likelihood term, it also is known as data generating model. But why is that? It is because it tells us how likely it is for this 100 coin tosses to be generated from a particular coin type, right? Understand that likelihood is not probability in the true sense because it does not sum up to 1. It does not sum up to 1. It simply tells us which value is bigger. Okay, now let's see another example. Obviously, you now can see that things are not as simple, but it's not that complicated as well. So let's see another example. So this time, suppose we have n words of an email as our feature set. So we can say the words are x1, x2, x3 up until xn, so x1 to n. So we have to predict whether this email is spam or non-spam. So S or N, given that we have these words, right? These words are observations. And the output, we can just denote it as Y. So these are the two things we have to calculate. We have to calculate probability of Y equal to S. That means probability of email being spam, given the words, probability of email being non-spam, given the words. And we have omitted the normalizing constant because it will be the same for both cases, and we have kept the other things, the likelihood and the prior for both cases. Okay, so the prior, let's start with the simpler things. The prior will be probability of an email being spam. It is nothing but the number of spams you have obtained so far divided by total number of emails you have obtained. And similarly for non-spam is the number of non-spams versus number of total. Now suppose you have just started your analysis of emails and you don't really have enough email samples at the start. In that case, you can omit the prior as well. But after a certain period of time, when you have thousands of emails, obviously you should inject some prior because we already know from prior knowledge that there will be a lot less spam emails compared to non-spam emails, right? Okay. So the non-spam email should have higher priority, higher probability. Okay, now let's look at the more interesting thing, which is the likelihood. So this is the likelihood term. So the likelihood term would be calculated like this: probability of x1 to n, that means probability of the words being x1, x2 up until xn. Given that our email is spam, this will be nothing but the product of these things. And similarly, in case of y equal to n, this will be the product of these things. Now, if you are clever enough, you understood already that this formula just came out of the blue. I haven't really given any proof of this formula. Why would this formula work? This is true. Actually, we are making an assumption here. We are saying that we have a conditional independence assumption. So what does that mean? We are assuming that given that we know which is our email type, the words in the email does not really have any dependency on one another. That means word 1 doesn't depend on word 2, word 3 or anything else, given that we have the email type, right? Now, this assumption doesn't always hold, but in many cases, it makes our life easier. Okay. But the question is, what if we don't want to put this assumption? What happens then? In that case, the formula changes. First of all, let's break this down. So x1 to n, we can just like expand it. And obviously the email is spam. So we can put the spam email here as well. This will be AND condition given y equal to s. And now if we want to break this down without any assumption, this is what it looks like. Probability of x1 given s, probability of x2 given x1 and s, probability of x3 given x1, x2 and s, and so on and so forth. You can already understand that it is quite hard to estimate these things from available data alone. Too many dependencies and it is not practical. There is an intermediate solution, that is, you can create a feature tree where each of these words depends only on a small subset of words, right? You can create this tree and then you can write this formula. Okay, so this is one example of using multiple features for predicting a certain class, right? Okay, so one last example. So here we have the height and weight of 100 men, and what we want to do is we want to predict whether these men are from India or Pakistan, given their height and weight. Now, what is so special about this problem? The specialty about this problem is height and weight, they are actually continuous variable, right? That means weight can be 50.33335 or 49.001, etc. Many other things. Okay. Very same thing. We have to first get the probability of y equal to I given w1 h1. If we are considering the first man among this 100 men. We also have to get the probability of y equal to p given w1 h1. I haven't written that here because you already know what to do. So if we want to get the probability of y equal to y, which is the prior, we can just do this division, number of Indian men versus number of total men. Then we have this thing right here. We have the likelihood term. This is the likelihood term. So if we assume the conditional independence assumption, then we can just break this down like this, right? So W1 and H1 are not dependent given that y equal to I. So we can just break this down as a product. The real question is, how do we estimate probability of W1 given y equal to I and probability of H1 given y equal to I? The answer is simple. We are going to assume that W1 or W, I mean any weight, stems from a PDF. That means probability density function of continuous distribution. So let me elaborate what I mean. So first what we are going to do is, since y equal to I here, right here y equal to I, that means it's an Indian man. We are assuming that the weight is from an Indian man. We can first find the mean, nu wi, and standard deviation, sigma wi, of all the weights of all the Indian men that we have, right? And then we can assume that all these weights are coming from a normal distribution where the mean is this and the standard deviation is this, right? And then we can simply get FW1, which is the density of this distribution for the W1 point, and that is going to be our probability value. We can do the same thing for height. We can get the mean and standard deviation for Indian man height. We can create the normal distribution and get the H1, right? So that is how we are going to handle the continuous case. So I hope that from this lecture, Bayes theorem is crystal clear to you. So if you like the video, please feel free to subscribe and share. And you can donate to our channel if you want to help our channel grow further. Thank you very much.